When designing electrical systems for multi-story condo or apartment buildings, a key decision involves the distribution voltage and the type of bus duct system employed. The choice often boils down to two primary options. Firstly, a 480 volts bus duct with step-down transformers located throughout the building, and secondly, a 208Y/120 volts bus duct fed by a single large transformer. Each option presents its own set of advantages and disadvantages, which must be carefully weighed against the specific requirements of the building and its occupants. Let's examine the first option, which is the 480 volts bus duct with step-down transformers. One of the primary advantages of using a 480 volts bus duct is its higher efficiency, especially over long distances. At higher voltage levels, the current is reduced for the same amount of power delivered. This lower current translates directly into reduced conductor size requirements for the bus duct, which in turn lowers material costs and installation expenses. Furthermore, the use of step-down transformers located near the load centers, which are the individual condo or apartment units, minimizes voltage drop and associated power losses. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. By placing the transformers closer to the loads, the length of the low voltage runs is minimized, by reducing voltage drop and improving overall system performance. However, the 480 volts bus duct with step-down transformers option also presents certain disadvantages. A significant drawback is the need for multiple step-down transformers, which increases the initial capital investment and the complexity of the installation. Each transformer requires space, protection devices, and regular maintenance, adding to the overall costs and effort. Additionally, the presence of multiple transformers can potentially introduce harmonics and interference into the electrical system. Harmonics are distortion of the voltage and current waveforms that can cause equipment malfunction, overheating, and reduced power quality. Mitigation techniques such as harmonic filters may be necessary to address these issues, further increasing the cost and complexity. Now consider the second option, which is the 208Y/120 volts bus duct with a single transformer. The most notable advantage of this option is its simplicity. With only one large transformer located in the basement or electrical room, the installation is generally less complex compared to the multiple transformer scenario. This simpler configuration also reduces the potential for harmonics and interference, as there is only one source of harmonic distortion. Furthermore, the 208Y/120 volts bus duct system requires less space for transformers, which can be a significant consideration in densely populated urban environments. On the other hand, the 208Y/120 volts bus duct option suffers from higher current draw on the bus duct for the same amount of power delivered compared to the 480 volt system. This higher current necessitates larger conductor sizes for the bus duct, which increases material costs and installation expenses. Moreover, voltage drop and losses can be more significant with the 208Y/120 volt system, especially over longer runs. The lower voltage level means that the same amount of power is delivered at a higher current, which exacerbates voltage drop problems. In some cases, voltage boosting or compensation techniques may be required to maintain acceptable voltage levels at the load centers, adding to the complexity and cost. In determining the optimal choice between these two options, several factors must be taken into account. The size of the building and its overall load requirements are critical considerations. For large buildings with high power demands and centralized load centers, the 480 volts bus duct with step-down transformers option may be more efficient and cost-effective in the long run. The higher voltage reduces current, minimizes conductor size, and reduces voltage drop, leading to lower operating costs and improved system performance. Conversely, for smaller buildings or buildings with distributed load centers, a 208Y/120 volts bus duct with a single transformer may be simpler and less expensive to install. The lower voltage system is easier to manage and maintain, and the reduced space requirements can be a significant advantage in certain situations. Another important factor is the distance from the transformer to the load centers. As mentioned earlier, voltage drop is directly proportional to the length of the conductor. If the distances are relatively short, the 208Y/120 volts system may be acceptable. However, if the distances are long, the 480 volts system with step-down transformers is generally preferred to minimize voltage drop and maintain acceptable voltage levels at the loads. The available space for electrical equipment is another crucial consideration. The 480 volt system requires multiple transformers, each of which requires a certain amount of space. If space is limited, the 208Y/120 volt system with a single transformer may be the only viable option. Conversely, if space is not a constraint, the 480 volt system may be more attractive due to its efficiency advantages. Cost considerations are always a major factor in any electrical design project. The 480 volt system typically has higher upfront costs due to the need for multiple transformers and more complex installation. However, the lower operating costs due to reduced voltage drop and losses can offset these higher upfront costs over the lifespan of the building. The 208Y/120 volt system generally has lower upfront costs but may have higher operating costs due to increased voltage drop and losses. A thorough cost-benefit analysis should be performed to determine the most economical option over the long term. In addition to these factors, several other considerations should be taken into account. Metering is an essential aspect of any multi-unit residential building. Both the 480 volts and 208Y/120 volts options allow for individual metering of each unit using sub-metering modules. These modules can be installed at each load center to measure the energy consumption of each unit, allowing for accurate billing and energy management. Power quality is another important consideration, especially when using multiple transformers. As mentioned earlier, harmonics and interference can be a concern with multiple transformers. Mitigation techniques such as harmonic filters may be necessary to address these issues and ensure that the electrical system operates smoothly and reliably. Energy efficiency is a growing concern in modern building design. Energy-efficient LED lighting and other measures can help reduce electrical loads and improve overall efficiency. These measures can be implemented regardless of whether a 480 volts or 208Y/120 volts system is used. Safety is of paramount importance in any electrical installation. Proper ventilation and temperature monitoring are crucial for electrical rooms housing transformers and bus ducts. Transformers generate heat during operation, and it is essential to ensure that the electrical room is adequately ventilated to prevent overheating. Temperature monitoring systems can be installed to provide early warning of potential problems, allowing for timely intervention and preventing equipment damage or failure. It's also important to ensure that the electrical installation complies with all applicable codes and standards. The National Electrical Code, or NEC, provides detailed requirements for electrical installations, including conductor sizing, overcurrent protection, grounding, and safety measures. Adherence to the NEC is essential to ensure the safety of building occupants and the reliable operation of the electrical system. Now let's delve a bit deeper into the technical aspects of bus duct systems. A bus duct, also known as busway, is a prefabricated electrical distribution system consisting of copper or aluminum bus bars enclosed in a protective housing. Bus ducts are used to transmit electrical power over long distances and to distribute power to various loads within a building. Bus ducts offer several advantages over traditional cable and conduit systems. Firstly, bus ducts have a higher ampacity, which is current carrying capacity for a given conductor size compared to cables. This means that bus ducts can carry more current without overheating, making them suitable for high current applications. Secondly, bus ducts have lower impedance compared to cables. Impedance is the opposition to the flow of alternating current. Lower impedance reduces voltage drop and improves system performance. Thirdly, bus ducts are easier to install and maintain compared to cables. Bus ducts are prefabricated and modular, which simplifies installation and reduces labor costs. Maintenance is also easier because the bus bars are easily accessible for inspection and repair. Bus ducts are available in various configurations, including feeder bus, plug-in bus, and trolley bus. Feeder bus is used to transmit power from the service entrance to the main distribution panels. Plug-in bus has openings along its length to allow for the connection of branch circuits. Trolley bus is used to supply power to moving loads such as cranes and hoists. The selection of the appropriate bus duct configuration depends on the specific application and the load requirements. When designing a bus duct system, several factors must be considered, including the ampacity, voltage drop, short circuit current rating, and environmental conditions. The ampacity of the bus duct must be sufficient to carry the maximum load current without overheating. The voltage drop must be within acceptable limits to ensure that the loads receive adequate voltage. The short circuit current rating must be high enough to withstand the maximum fault current that could occur in the system. The environmental conditions, such as temperature, humidity, and corrosive elements, must be taken into account to ensure that the bus duct is properly protected. Now let's talk about transformers. A transformer is an electrical device that transfers electrical energy from one circuit to another through electromagnetic induction. Transformers are used to step up or step down voltage levels, isolate circuits, and provide impedance matching. Transformers consist of two or more coils of wire wound around a common core. The primary coil is connected to the source voltage, and the secondary coil is connected to the load. The ratio of the number of turns in the primary coil to the number of turns in the secondary coil determines the voltage transformation ratio. Transformers are available in various types, including dry-type transformers, oil-filled transformers, and cast-resin transformers. Dry-type transformers are commonly used indoors because they do not contain flammable oil. Oil-filled transformers are used outdoors or in special enclosures because they are more efficient and have a higher overload capacity. Cast-resin transformers are similar to dry-type transformers but use a cast-resin material to encapsulate the core and coils, providing improved insulation and protection. When selecting a transformer, several factors must be considered, including the voltage rating, power rating, impedance, and efficiency. The voltage rating must be compatible with the source voltage and the load voltage. The power rating must be sufficient to supply the maximum load demand. The impedance must be appropriate for the application to minimize voltage drop and ensure proper operation of protective devices. The efficiency must be high to minimize energy losses and reduce operating costs. Now let's address harmonics. Harmonics are sinusoidal waveforms that are integer multiples of the fundamental frequency. In a 60 Hz system, the fundamental frequency is 60 Hz, and the harmonics are 120 Hz, 180 Hz, 240 Hz, and so on. Harmonics are caused by nonlinear loads such as electronic devices, variable frequency drives, and saturated transformers. Harmonics can cause a variety of problems in electrical systems, including equipment malfunction, overheating, increased energy losses, and reduced power quality. Harmonic currents can overload neutral conductors and transformers, leading to premature failure. Harmonic voltages can distort voltage waveforms, causing malfunction of sensitive electronic equipment. To mitigate harmonics, several techniques can be used, including harmonic filters, line reactors, and harmonic mitigating transformers. Harmonic filters are used to block harmonic currents from flowing into the electrical system. Line reactors are used to reduce the magnitude of harmonic currents generated by nonlinear loads. Harmonic mitigating transformers are designed to reduce the generation of harmonics within the transformer itself. The selection of the appropriate harmonic mitigation technique depends on the specific application and the severity of the harmonic problem. Now let's discuss metering. Metering is the process of measuring electrical energy consumption. In multi-unit residential buildings, individual metering of each unit is essential for accurate billing and energy management. Sub-metering modules are used to measure the energy consumption of each unit. These modules can be installed at each load center to provide accurate readings of kilowatt-hours, kiloVARs, and other electrical parameters. Sub-metering modules can be connected to a central data acquisition system to collect and analyze energy consumption data. This data can be used to identify energy-saving opportunities, optimize building performance, and improve tenant billing accuracy. Sub-metering modules are available in various types, including electromechanical meters, electronic meters, and smart meters. Electromechanical meters are traditional meters that use rotating discs and gears to measure energy consumption. Electronic meters use electronic circuits to measure energy consumption and provide more accurate and reliable readings. Smart meters are advanced electronic meters that can communicate with a central data acquisition system and provide real-time energy consumption data. The selection of the appropriate sub-metering module depends on the specific requirements of the building and the desired level of accuracy and functionality. In summary, the choice between a 480 volts bus duct with step-down transformers and a 208Y/120 volts bus duct with a single transformer depends on a variety of factors, including building size, load requirements, distance from transformer to load centers, available space, cost considerations, power quality concerns, energy efficiency goals, and safety requirements. A thorough engineering analysis should be performed to evaluate these factors and determine the optimal solution for each specific project.